Okay, today we are looking at problem 19 from the free response review. This is a problem that we have seen before. This is a table problem, so make sure that you have done this problem before watching this video. Let's get it going. So we have this rocket with a positive velocity that's being launched, from a height of 0 times 0. And they give us this basically this table for time from time 0 to 80. And let's talk about what we're seeing now. I want to remind you, the very first time you see a function, a table, or a graph, or anything like that, you have to ask yourself what you're looking at. Am I looking at a position function, right? So, f of x, a derivative function, f prime of x, or a second derivative function, acceleration function, f double prime of x. In this case, we are looking at a velocity function, right? So we're looking at a derivative, right? So usually the way they do it in terms of heights, the position function would be s of t. This is the velocity function, v of t, and the acceleration function would be a of t. So again, we are looking at a velocity function. This is giving us, velocities, not height values or position values. That being said, let's move on. Find the acceleration of the rocket over time 0 to 80. Okay, so we're looking at the acceleration. They gave us a velocity. We're going down one, right? We're thinking derivative-wise. In this case, though, it's not a derivative, though, because we're looking at the average acceleration from time 0 to 80. So in other words, the average acceleration, if I can spell the word average and acceleration, is going to be equal to v of 80 minus v of 0 from 80 minus 0. Basically, right, the average acceleration is just the slope of the line from these two endpoints. So in this case, we would get 49 minus 5, right? V of 80 is 49, v of 0 is 5 over 80 minus 0, okay? So that would be 44 over 80. If we wanted to simplify that, we could, but there isn't any reason to. So what are our units here? And then it says indicate units. So let's think about this. We are looking at an average acceleration. What did we do? We took the velocity and divided it by time. So our units are going to be feet divided by time twice, so seconds squared. Okay, let's move right along. Using correct units, explain the meaning of that thing in terms of the rocket's flight. Use a midpoint Riemann sum with 3 subintervals of equal length to approximate that value. Okay, I'm going to start with approximating this, and then I'll do my explanation second. So we want to find this, okay? We want to find this. And as we know, we've seen this before, we basically want to, in order to evaluate that, right, what do? When we were doing trapezoid rule, we added up a bunch of trapezoids. In this case, we're doing midpoint rule. And the midpoint, we're breaking this up into 3 sections from 10 to 70. So in other words, see if you guys agree with me, 3 equal sections. So I'm looking at, think of it like, these are my different rectangles. Rectangle 1 goes from 10 to 30. Rectangle 2 goes from 30 to 50, and then rectangle 3 goes from 50 to 70, right? See if that makes sense to you, okay? So let's see what we got here. In order to find the area of each of these rectangles, well, first off, because they all have the same base, right? Each of these bases, 30 minus 10 is 20, 50 minus 30 is 20, 70 minus 50 is 20. Each of these bases are the same. I'm going to pull the base on the outside. Now, when we're looking at midpoint, right, if I want to find the midpoint of a rectangle, so this is the left-hand side of the rectangle, this is the right-hand side of the rectangle, this is the midpoint of the rectangle. So I'm using the midpoint to evaluate the height. So in other words, I'm going to be doing v of 20 plus, let's go to the next one, right? Left-hand side, right-hand side, so this has to be the middle of it. So v of 40 plus, again, left-hand side, right-hand side of rectangle, v of 60 is the middle part. Okay, so that gives us 20 times v of 20 is 22, v of 40 is 35, and v of 60 is 44. Okay? So, let's see. They asked us to do a couple other things, so let's make sure we've answered the question. So they want us to use units. Okay, so let's think about what we did. We took v of t, which is a velocity function, and we integrated it, right? So we moved up. So this has to be a position value. So this has to be feet. Okay, what's our description here? Well, right, this is a displacement function, right? A definite integral gives us a displacement from time blank to time blank. So in other words, what I'm going to say is this thing right here represents, I'll say it first. It represents the change in the rocket's height, right? It change in a rocket's height from time 10 to time 70, okay? So represents the change in the rocket's height from time t equals 10 to t equals 70. So a couple things that's really, I'm going to say t equals in feet. This is probably not important because I've already put the feet here, so they're going to grab the units from there, but I'll just say it to be complete. Okay, a couple of things I just want to point out to you before we move on to the next part. So when you're doing your explanation here, there's a couple things that are important. One is it really is important that you give your time interval, right? This is a definite integral, so you need to say it starts at A, it ends at B, right? You just need to indicate that you're recognizing that those parts, that the limits of integration are important, okay? So you got to talk about them. So it starts at time 10, ends at time 70, and then again, what is it a change in? It's a change in the distance, or it's basically a change in the position. So I said it's a change in height, but you could have said it's a change in the distance, what have you. Okay, let's move on. So rocket B is launched upward with an acceleration, a of t, of that function in feet per second per second. So this is an acceleration function. Be careful. At time t equals 0, the initial height is 0. So it's basically telling us it starts at a height of 0. Right, at time 0, and then it's got an initial velocity of 2 feet per second. Which of the two rockets is traveling faster at time 80? So here's what their question is, right? We have rocket A, right, at time 80, and we have rocket B at time 80, and we're looking at the velocity, right? We're looking at the velocity of each of these, and we're saying which one is a bigger number, right? Which one was going faster, right? Let me just make sure that's what it says. Yes, which is traveling faster. So velocity A is easy peasy, right? The velocity at 80 for rocket A is 49. We know that, okay? So I'm gonna just put a note to myself so I don't forget. So velocity of A, that's easy. That was just given to us in the table. But what about velocity B? Well, I think you guys would agree, if this is the acceleration, we should be able to go and figure out what the velocity is. So let's do it. I want to remind you about pointing. So I'm going to use a B here. So the velocity of B, of t, dt, excuse me. I'll actually just say the velocity of B is going to be the integral, right, of a of t dt. Okay, we're going to integrate that, and then we'll be plugging in our specific point, which is our 2 feet per second at time 0. So in other words, we will then be plugging in this point. Again, this is a velocity point. So let's go and do this. So let's first off, let's integrate this. So our function, I'm going to pull that 3 out right off the bat if you guys don't mind. And if you do mind, say something right now. Oh, you didn't say something? Okay, then you don't mind. Perfect. Okay, so let's see. I'm going to do a little u substitution. So u equals t plus 1, du equals dt. So this is going to be 3 over du square root of u. And actually, let's do a little rewrite on that. Let's write this as u to the negative 1/2 du. Okay, so when we integrate this, we get 3 times, let's see, this is going to be 2u to the 1/2 plus some c, right? That's important, that plus c. See how this recurring theme, that plus c is so important over and over and over again? We've seen it in the last 3 problems. Again, don't forget it's such a big deal. And the reason is, this gives us our family of functions, right? What we want to do is we want to find out what is our specific function. So now what I'm going to do, let's just bring that v of b down. Now what I'm going to do is I'm going to plug in that initial condition. So at time 0, v of b equals 2. So 2 equals 3 times, oops, before I do that, let's write our v of b function actually. Let's put it back. Let's do our substitution. So just so I don't lose anybody here. So v of b, t equals 3 times 2 is 6 times the square root, and u was t plus 1 plus c. There we are. Okay, now let's plug in our initial condition. So our initial condition is this, and it was at time 0, so 0 plus 1 equals plus c. So this gives us 2 equals 6 plus c. So I think you guys would agree c equals negative 4. I'm going to move this stuff over. I'm kind of running out a little bit of room here, and I don't want to go crazy. And that equals c, not 4. I don't know why I wrote that down. Okay, so let's put our function together. So the b function, I think you guys would agree, is going to be 6 times t plus 1, and the c is minus 4. Okay, so now what do? We evaluate this at 80, right? We want to know what is its acceleration at 80, and I think you guys would agree. That's going to be 80 plus 1 minus 4, so this is going to be 6. The square root of 80 is 9 minus 4, so this is 50. So now, look what we have, right? And I'll just put it in here. I'm going to summarize it. But we have the velocity for rocket B at 80 is 50. The velocity for rocket A is 49. So now we're going to make our conclusion. Rocket B is faster at time t equals 80. And why is that? Because v of b of 80 equals 50, which is greater than 49, which equals v of a of 80. Okay? That's all there is to it. I will see you in the next video. Sorry, I'm trying to make that v look more like a V.